Hello, and welcome to the Productionizing Ethical AI Credit Scoring talk at the AIS 2022. So I'm going to talk a bit about the challenges we typically face around putting fair ML scoring models into production and how Delta Lake Feature Store and MLFlow can help. So a bit about me. I am a specialist solutions architect at Databricks. Most of my day-to-day is spent helping customers optimize their machine learning operations, and it is a lot of fun getting to see different setups and working with different companies. A fun fact about myself is that I graduated with a degree in plant sciences and zoology. Some of the projects I used to work on involve studying photosynthesis in rice and also cancer pathways in B-cell lymphoma. That sounds very different to working in technology, but I think a unifying theme throughout my working life has been my desire to create a positive impact through my work. Which brings me to our topic today. So this is an overview of what we want to cover. We'll start with just setting the context and the background to what we want to discuss. So why should we care that our credit scoring AI systems are fair? What are some of the causes of bias and unfairness that can creep in? And then after that, we'll move on to look at the current state of play within the industry right now. We're going to cover some existing solutions that we have to mitigate unfairness, and these can include things like specialized metrics that allow us to calibrate our model's predictions, and also having frameworks released by financial regulators to align all the FSIs around the same ideas. Then after covering existing work, we're going to focus on some of the challenges that are currently holding us back. Spoiler alert, a lot of this actually centers around challenges of implementation, mainly optimizing and automating the machine learning lifecycle so that it's traceable, auditable, and transparent. So moving on. Why should we care that automated credit scoring systems are fair and ethical? Well, simply put, these are very high-stakes systems. Someone's credit score can determine whether or not they get a housing loan, whether or not they are employable. However, it is known that these models and systems can systematically disadvantage vulnerable groups, especially if these groups have historically been underbanked and there's a lack of data, or these populations may simply be unaware of how to build a good credit score. So it's very important to measure how our systems may be denying opportunities to certain groups based on factors that may be out of their control, such as their education level and their race. So why can AI-driven credit scoring systems be unfair? Well, the first reason, and this is a reason that I think people may be more familiar with, is that our models are biased because the data that we use to train them is biased. So a recent paper published by a Stanford researcher shows that for historically underserved groups, credit scores are actually quite noisy indicators of whether or not someone will default on their loan. And these researchers report that it's really not that the model cannot fit the data, but that there's poor quality credit data for these historically underbanked subpopulations. So if the data that we have is poor, then the output that our model has also will be unreliable. Perhaps more insidiously, despite extensive reporting on biased algorithms in the news, there's actually remarkably little consensus or concrete definitions on what bias and unfairness really mean. So in a recent paper published by the ACL in 2020, researchers found that up to 146 papers focused on bias in NLP systems actually had vague and inconsistent motivations. It also doesn't help that previously qualitative ideas such as creditworthiness now have to be quantified by models. So it's not very helpful when you're trying to solve a problem but don't actually have a clear definition to work with. But the reason that I particularly want to highlight in this talk is one that we don't talk about enough, which is the lack of practical, actionable, and industry-approved guidelines for putting fairer systems in place. And we can really see this implementation gap when we compare the left and right columns on this slide. So on the left, we can see that there is extensive treatment of fairness within the academic literature. We have proposals for fairness-aware algorithms, for better ranking systems, and most AI and ML conferences today have a special track discussing the issue of fairness. But if we look to the right, where we look for industry and regulator-approved frameworks, the list is actually much shorter. There's a paper released by the Monetary Authority of Singapore, some framework also released by the Financial Conduct Authority in the UK, but compared to the research and attention FAIR ML has received in academia, industry, AI, and ML actually has a lot of catching up to do. So nevertheless, there is still some early work in this area. And we can break this down into, firstly, fairness-aware metrics, and also some regulatory frameworks that have recently been released. So let's look at fairness-aware metrics first and how they compare to a completely naive system. So we can think of a naive system as a system where we don't apply any fairness-focused metrics, and we focus mainly on maximizing profit. So in this case, we have a hypothetical scenario where we allocate credit scores from between 1 and 100. And we say that applicants will be granted a loan if their credit score is above a certain threshold. So for the blue group, this threshold is a score of 61, while for the orange group, this threshold is 50. And these are thresholds that will yield the highest profit. But because these groups have different thresholds, they are held to different standards. In this scenario, 60% of applicants in the blue group who would pay back a loan had their applications approved versus 78% in the orange groups, which does lead to different and unfair economic outcomes. So a slightly better situation would be to have a metric that equalizes the blue and orange groups in some way. One metric that tries to do this is called demographic parity. So under demographic parity, the percentage of successful loans in the blue and orange group are the same. So we see here that they're both 37%. However, there's a drawback to this metric, which is that this measure only accounts for the number of loans given, but not the rate at which these loans are paid back. In other words, we do not actually take into account who defaults and who doesn't. This means that actually fewer qualified people in the blue group, 64%, are granted loans compared to 71% in the orange group. So a further refinement on demographic parity is a metric that we call equal opportunity. So under this metric, among applicants who would pay back a loan, the percentage of a loan between the groups are equal. So here, as long as you are eligible individuals, regardless of your background, you're equally likely to be offered credit. In this case, it's 68%. So these are some of a few metrics that can begin to account for different groups in a population. It's important to note that none of these metrics are 100% comprehensive. So it's important to take into account a range of metrics when we evaluate our systems. And apart from metrics, there is also some work on certain formal methodologies or checklists released by regulatory authorities. So one such example is the Veritas framework from the Monetary Authority of Singapore. And although this framework was developed within the ASEAN region, it is applicable to different jurisdictions. So it outlines how FSIs should begin to think about concepts such as fairness, ethics, accountability, and transparency when it comes to AI. And some questions that they urge FSIs to consider include, have you thought about the trade-offs that exist between maximizing your commercial metrics versus making sure that subpopulations are not discriminated against? And if you choose to use certain protected attributes such as personal information, have you implemented any corrective procedures to improve fairness for certain groups that are known to be traditionally at a disadvantage? So, given this state in the industry right now, what are some remaining challenges? And I think this quote from FICO AI Research sums this up pretty well, which means, how do we begin to actually incorporate these concepts such as corrective procedures and post hoc calibration into our machine learning system such that it is repeatable and running smoothly in production? So, in other words, how might we orchestrate our workflows to reflect our commitment towards fairness? And we can begin to think about this by breaking down what we call a production-ready credit scoring system into 3 areas. We can say that the system should be reproducible, which means the parameters, the code, and the data that we use to develop the model should be versioned. And even more than that, any feature engineering logic or pre-processing should be consistent between both training and serving. Secondly, we shouldn't rely on vague and inconsistent definitions of fairness, but make sure that we can put a metric to fairness and measure this before we actually push the system into production. And the journey doesn't only end when we deploy our model. We should also continue to monitor whether our protected variables, such as gender or marital status, are experiencing data drift. And this involves having robust monitoring systems in place. Finally, our system should also be auditable, and this means we can, if a financial regulator requests it, backtrack to a former model that was trained in, say, last month or last year, and then be able to pull out the code parameters and feature engineering logic that we use to train the model. So how does this translate into code? Well, we have a demo to show that. Okay. So this is a workflow of what such a system would look like on Databricks. Starting from the top, we can ingest our data and pass in our raw data through the medallion architecture, where we have our bronze tables, then we clean our data, and we have our features that we then store inside Feature Store. After training our model, we should version any fairness-relevant metrics and artifacts into our MLFlow run. Then, when we transition our model to staging from within the MLFlow model registry, we can make use of Databricks model registry webhooks to actually kickstart several downstream pre-deployment checks. In this case, firstly, we send a Slack message to a model approver notifying them of this transition request to production. And secondly, we will also kickstart a validation notebook job that can automatically generate any fairness-related reports and visualizations for this model approver to properly look at. Then finally, if our model passes our checks and it moves into production, we also need to set up robust monitoring processes to monitor our model for drift. So in this case, we will use the credit card training data set from the UCI machine learning repository. This data we will take and use to train a binary classifier that predicts whether or not a customer will default on his or her credit payment in the next month. So in the real world, this is the sort of model that may typically influence a loan decision-making process or a credit score. So I'm going to move now to the second notebook, and for this notebook, we have in the beginning already ingested and cleaned our data through the bronze and silver tables, and now we're going to create a few features with Feature Store. In this case, what we're going to do is we're going to count the number of times a customer met their payment obligations over the past 6 months. And our second feature is going to be the number of times they did not meet their payment obligations over the first time period. After we've defined functions for calculating these features here, we will then write these features into a feature store table so that when we train our model and when we serve it, we can be sure that these logic holds the same between training and serving, and there is no skew involved. Then after we've defined our features, we will then train a model and log our fairness metrics with MLFlow. So to help us with this, given the huge range of fairness metrics out there and the different ways of looking at fairness, we are going to make use of an open source package that was actually released by, again, the Monetary Authority of Singapore. This package is on GitHub, and it provides really good helper functions for just auto-generating fairness metrics and visualizations for a model. So in order to use this package, we first need to define what we call our protected variables, which are input features that should not unduly bias our model. Over here, we will set somebody's sex and marital status as protected variables. And within these protected variables, what we then do is define what we call protected groups, which is groups that we think should be privileged or unprivileged based on our domain knowledge. So in the case of the sex variable, we will set male segment to be the protected variable, and in the case of the marriage segment, we will set married as the protected variable. And these are not set in stone. It should be a discussion between business SMEs and also based on historical data. Then we pass the training data, protected variables, and groups into our model container object here, which we have inside our MLFlow run. And later we specify that we want to use this model container for credit scoring. And when we call evaluate on this credit scoring object, we will automatically generate our fairness evaluations as JSON files, which we can then version in MLFlow to be analyzed later. This is very convenient because for every model that we generate, we call evaluate, and the resulting artifacts will be saved as MLFlow artifacts as part of the model run. So at this point, we've basically managed to cover the reproducibility aspect of what we earlier defined as our production-ready credit scoring system. And having a reproducible system here means that further down the road, if we are subject to auditing, or if a customer, for example, requests more transparency into their loan decision, we can backtrack to the model and any evaluations that we ran on it. But the productionization process doesn't just end at the model training stage. So at this point, a data scientist or a machine learning engineer will typically transition the model into a staging environment before executing some checks and validation before the model is pushed to production. So to automate this project, we're going to make use of Databricks model registry webhooks. And what are webhooks? So we can basically split webhooks into either job webhooks or HTTP ones. And job webhooks allow us to trigger a notebook job when a model transition request is made. And also, HTTP webhooks allow us to make a call to any third-party service that accepts an incoming request. So in our case, we set up an HTTP webhook to give us a Slack notification when a transition request is made to move a model into production. And we also set up a job webhook that triggers a notebook job to generate a fairness report. And over here, you can see that we have a registered model in the staging environment, and we can request to transition this to production. And I don't know if anyone heard the Slack notification, but it was there. So now I'm going to put myself into the shoes of a model approver. I just got pinged on Slack. So what should have happened also is that we see we have a job that got kicked off by our webhook, and it's currently running. Eventually, what it will generate is the output of a notebook here, where we can see that we have our report generated. So what does this report actually mean? And how can we begin to analyze our model based on the specialized metrics that we talked about previously? So one way of looking at this is to use something called a parity measure. Basically, we can take any metric that we covered previously, such as demographic parity or equal opportunity, and then we compare the difference in approval rates between the privileged and underprivileged groups, which we had also defined earlier. So we can see that for the sex-protected variable, there was a difference of negative 0.01, which doesn't seem very significant. Maybe we can let that pass. And then for the protected variable, actually, there's a difference of about 0.02. So a portion of this validation process can actually be automated. So on one hand, I, as the model approver, can visualize the parity measures in this notebook. But we can also set some automated checks here, where we say that the difference in the parity measure should not exceed a certain threshold, for example, 0.1. So if the parity measures pass these tests, what we do here is that we write the passing test as a tag back into the MLFlow model registry UI. So if I click these tags here, we can see that the parity check for both protected variables passed. So this is a very quick and easy way of also automating some checks where we can actually save a model approver some time. Then, apart from a parity check, what we can also do is to look at the performance metrics of our model, just to get a sense of how it's performing. And also, more than that, what is the trade-off between fairness and profit? So we can see here, for example, if we only have a single threshold for both the privileged and unprivileged group, we have a best balance accuracy of 0.56. And if we actually have separate thresholds for the privileged and unprivileged group, we will actually have a higher balance accuracy of 0.6. So this can give a starting point for a discussion with maybe the business SME, who may be able to inform us better on whether or not we should be using a single threshold or separated threshold. And finally, we have a conclusion which may miss some nuance, but sometimes that's also useful to know, which is like at a threshold of 0.43, we decide that even by incorporating protected variables such as someone's marital status, our model is still fair. So finally, we can save our fairness metrics and model metadata into a Delta table to keep track of its deployment history. We can see we have our model name, the version, the runtime of it, and further down the road, if we are ever called upon to revisit this model, we have the metadata saved and we can extract based on the model name and other metadata, the actual model from within the model registry. So right now, we've also shown how we can begin to quantify our system with fairness metrics. And we've also managed to create a system where we can go back in time and look at previous models, searching for them. So finally, we are going to cover how we can monitor these protected variables in production for production drift. And mainly, most monitoring processes can be broken down into this workflow. Model monitoring basically means having a baseline data set. Usually this is the data set that was originally used to train the model, and any newer incoming data. Then what we want to do is to take this baseline data as a reference and compare that to the incoming production data. Given this comparison, we can then calculate various drift statistics. We can look at whether or not the label distribution has shifted significantly, whether or not the features have drifted, and also whether or not the quality of our data has actually gone down from when we trained the model. We don't cover this in this demo, but if we really wanted to, also we could set up a dashboard to visualize these models from different angles. For example, if you have multiple models, you can compare the models with each other, or you can look at monitoring the model through time, so you can look at trends. The important thing here is that some models are more volatile than others, so it's quite important to empirically validate what actually is drift. Because if you get a significant drift p-value, that doesn't necessarily mean that you do need to retrain or rework the model, especially if the model historically has actually been quite fluctuating up and down without a significant business impact. So we're going to set up monitoring here by registering the model and the project we want with a little helper class that we've created. And then we're going to log some new incoming data, which we say 6 months later, we get a new data set and we add this to our baseline data table. Then finally, we're going to use an open source model monitoring package to start looking at some visualizations. And we can see for our features here, we do not have significant drift in this scenario. Only 1 out of 7 features have been detected to have a significant drift score over here. And this is a p-value that should be significant if it's more than 0.05. But if we look at these two variables, we can see that the true labels seem to have shifted between the baseline data and the new data. However, our predictions actually have remained about the same. So is this something that we want to look at? Possibly, and the first indicator that something interesting is going on is this drift visualization and the p-value. Another visualization that we can look at also is whether or not our labels have drifted. And in this case, we see that yes, the reference data, which is in gray, seems to be a little bit different from our current data. And again, this is something that we may want to look at. So if we look a little deeper, we can validate our observation previously that actually amongst the predictions, there wasn't a lot of difference, even though the target itself seems to have changed. And if we want to, we can also look at how age has affected the target prediction and other variables such as someone's education or marriage. Finally, we can save these drift statistics into a delta table, again for tracking and metadata versioning. And another thing to look at also is to segment these labels and predictions by our protected variables, just to see whether or not our protected variables have been affected. And what we see here is that despite the seeming shift in our target variable, we don't actually see that there's any meaningful difference for our protected variables, both for the target and the defaulters. So at this point, we can decide whether or not we need to retrain the model, or we may decide that actually this is an acceptable amount of drift and we can let the system continue running as it is. So this is where our workflow ends. Obviously, there's also other considerations such as your retraining schedule. But I think the takeaway at this point also is to take a step back and realize that metrics and technology, which we've focused on a lot in this talk, are actually still only a few tools that we have to improve our machine learning systems. And ensuring fair systems will ultimately involve a much more multidisciplinary approach, from incorporating sociology and normative reasoning and philosophy, and not to mention law as well. So with that, I hope I gave everybody some food for thought, and I'll be happy to take questions.
Thank you, Jane. That was an important topic and you did an amazing job. So if anyone has any questions.
How do you deal with bias mitigation when you identify bias within your data?
The easiest way would be to calibrate your predictions in some way. So for example, if we want equal opportunities between groups, we can actually set different thresholds for the different groups so that we actually get equal outcomes. That's one way of doing it. Yeah.
Can I ask another question? It's okay. So I saw that you use Veritas as your kind of fairness testing package. Is there any particular reason why you chose that one, or have you considered other things like FairLearn or other kind of fairness testing packages?
I chose the Veritas open source package mainly because firstly it comes from a financial regulator itself rather than, say, a technology company like Google. And secondly, also, the Veritas toolkit is actually released with an actual methodology paper that was published. So the MAS in Singapore actually worked with a range of different banks to put together that framework. So the two are quite aligned. And to me, that really cements the fact that it's practical. Yeah.
Similar question, the open source model monitoring package that you use that looked like Evidently. I'm curious if you've used that with any client-sized data and any kind of challenges or successes you had with that.
Yeah. So Evidently is still in very early stages, and the writers of the package do acknowledge that right now it only runs in single node. You do have to convert your data frames into pandas. So I used it mainly for demo purposes. If you're interested, Databricks does have a production-ready model monitoring process in private preview. So yeah.
Probably we'll take this last question.
How different production version of this project is from a demo version that you have in the workbooks?
Apart from the monitoring visualizations, this is I've implemented similar workflows with clients, so I would say it's quite scalable. Yeah.
Maybe this is the last question, I guess. And if anyone has any questions, Jean has graciously agreed to answer them outside. So,
how do you deal with the explosion of complications when you have multi-dimensional factors that you have to take in? So let's say females are underprivileged, then what race they're underprivileged, so you could have like 130 races, 15 genders.
Yeah, so it can rapidly spiral out of control And I think this is why it's important to actually have guidelines that people can align on. So for example, within the methodology paper published, it is recommended that the amount of effort you spend on considering fairness should also be commensurate with the importance of the model. So for example, if you have a model that is about upsell recommendations, then the fallout from that model is not very heavy, so you don't actually have to drill down really deeply into like the actual sources of bias. But again, if you have a high stakes model, then the considerations are different.
Okay, we'll wrap the presentation. Thank you so much, Jane. Big round of applause.